Loud. I now call to order the Society's 2366th meeting in the 145th year since its founding in 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Carey Lisse. We'll begin with a few announcements, followed by a reading of the minutes of the 2365th meeting, a surprise announcement, and a brief recounting of the 28th meeting of the Society in 1872. We will then turn to this evening's lectures, followed by a question and answer period. Thereafter, I'll present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2016 and Spring 2017 lecture series, the Policy Studies Organization, in cooperation with the American Public University, and a new sponsor who's asked to remain anonymous. I am pleased to announce that the following new members have been elected to the Society: George Bren, a cardiologist, Wendy Makins, an artist, and Carey Lisse, tonight's speaker. Please join me in welcoming them to the Society. Before we turn to a reading of the minutes of the previous meeting, if I can find it, I'm very pleased to announce that a personal friend and a former speaker, Dr. J. Fraser Stoddard, was awarded the Nobel Prize yesterday for his work on, guess what, molecular nanotechnology. He was our president speaker at the 2294th meeting on Friday, January 6th. And there is Sir Fraser. We don't usually use honorariums on this side of the Atlantic, but I thought I'd make an exception. So we are very happy for him. And we'll be very happy if we can get back to our slide presentation. Let's see, where did it go? There we go. So we will now turn to the minutes of the previous meeting, which will be read by External Communications Director Preston Thomas. Preston?
At the Cosmos Club in Washington, D.C., on September 23, 2016, President Larry Milstein called the 2365th meeting of the Society to order at 8:08 p.m. He announced the order of business and welcomed new members. The minutes of the previous meeting were read and approved. President Milstein presented a summary of the 27th meeting of the Society, held in May 1872. President Milstein then introduced the speaker for the evening, Dr. Craig Kundrat, Life Sciences Lead and Lead Mission Scientist for the NASA Twin Study in the Office of the Chief Scientist at NASA. His lecture was titled, NASA's Kelly Twin Study, Characterizing the Effects of Spaceflight from Omics to Cognition. Dr. Kundrat began by explaining that Mars is the horizon goal for NASA, with manned missions planned for the 2030s. Preparations are already underway for the journey, and the Kelly Twin Study is a way to learn about how spaceflight affects what NASA refers to as the human system. The leading plan for a manned mission to Mars is a conjunction class or long stay mission, consisting of a 6-month transit to Mars, an 18-month stay, and a 6-month transit back to take advantage of favorable orbital alignment between Earth and Mars. The risks of such an extended mission would expose the crew to fall into 3 main categories: abnormal gravity, radiation exposure, and psychological effects. In microgravity and zero-G environments, sedimentation does not occur, so objects and substances do not fall as they normally would, including inside the body. Hydrostatic pressure is absent, which changes blood flow and affects fluid shifts. Convection also ceases, so heat dissipation becomes problematic. Radiation from solar flares is relatively simple to shield against. The real threat is galactic cosmic rays, which are the nuclei of atoms, from simple hydrogen up to ion, which are traveling at a fraction of the speed of light. Because GCRs can be so high energy, they are difficult to effectively shield from. GCR exposure for astronauts is approximately equivalent to a chest X-ray every 10 days. Psychological stressors for astronauts include isolated, confined conditions and social and environmental monotony. They will not have circadian cues, without which individual sleep-wake cycles can diverge dramatically. The international crew will also face interpersonal, cultural, and organizational factors. Preliminary studies on the physiology of spaceflight have shown predictable changes across multiple body systems, some of which equilibrate with time, and others, such as bone loss and radiation exposure, which show an incremental accumulation. To send a mission to Mars, scientists need to better understand the extent of these changes and the long-term effect on astronauts. In 2012, as astronaut Scott Kelly was preparing for his year-long mission to the International Space Station, he suggested the possibility of a study to take advantage of his identical twin, astronaut Mark Kelly, who would stay on Earth. NASA ultimately accepted proposals for a suite of studies that would leverage the plunging cost of genome sequencing to examine in minute detail the effect of space travel from the genome up to the level of the entire body. This omics-based analysis would provide insight into effects from cellular aging and regulation to organ systems such as immune function, the gut microbiome, and cognition. The major data collection for these studies is complete, and those samples will be processed by the end of the year, with analysis to begin in January and a combined paper planned for 2017. Dr. Kondrat noted that we have never before had such insight into the biological factors affecting the health of an individual, making this study a landmark in bioethics as well. For the study, NASA developed its first genetic research policy to address questions of privacy, publicity, medical usage, and the relationship between the researchers and subjects. Dr. Kondrat concluded by noting that Mars is the horizon destination for human exploration, and the Kelly twin study will help us to better understand the way spaceflight affects the many omics of the human system. It also provides a preview of the new social and ethical questions that emerging omics-based analyses will raise on Earth. After the conclusion of the talk, President Milstein invited questions from the audience. One questioner asked how samples of the astronauts' microbiome were preserved without disrupting the organisms to be studied. Dr. Kondrat explained that swabs of the sample are placed in a negative 80-degree freezer and that shotgun sequencing will be used to analyze all the DNA in the sample directly without requiring live microbiomes to culture. Another questioner asked why NASA is pursuing human spaceflight. Dr. Kondrat explained that NASA is doing a great deal of science with robots and that Mars is likely to be a combined mission with both robots and humans. For example, in areas with particular potential for evidence of life, robots may be used to avoid contaminating the site. Nonetheless, he noted, it is part of the human spirit to explore, and it would not be the same if we only ever sent robots. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:04 p.m., President Milstein adjourned the 2,365th meeting of the society to the social hour. Temperature, 23°C. Weather, clear. Attendance, 91. Respectfully submitted, Preston Thomas, External Communications Director.
Thank you, Preston. I think you left out a particular question there.
I did.
It was the sex question. Are there any corrections or comments on the minutes beyond mine? If not, I will entertain a motion from a member to accept the minutes as read. Do I have a second? All members in favor? Aye. Anyone opposed? Minutes are accepted as read and will be posted to the website in due course and hopefully eventually published in the new editions of the Journal of the Patent and Trademark Office. No, the PSW. I'm a patent attorney. Okay, the 28th meeting of the Society was held on Saturday, June 1, 1872. President Joseph Henry was in the chair. The bulletin does not report the location or the time of the meeting. Joseph Henry was a primary founder of PSW and served as its president from its beginning in 1871 until his untimely death in 1878. He was the preeminent American physicist of his time. In addition to founding PSW and serving as its first president, he also was involved in the founding of the Smithsonian Institution and served as its first president. He did seminal work on the fundamentals of electricity and magnetism, including particularly notable work on induction that led to improved magnets and generators and to the development of the telegraph. One of his most important practical contributions was his finding that a current flowing through an insulated conductor wound around a ferrite core induced a magnetic field, and that the strength of the field is proportional to the strength of the current, the multiplicity of the windings, and the properties of the wire and the ferrite core. And this allowed him to make very strong electromagnets, which were quite the marvel of the day. Grove Carl Gilbert reported at this meeting on the erosive effects of sand, not only on land, where it's driven chiefly by winds, but also in rivers, where he opined it is the chief agent of erosion. Gilbert was one of the most important figures of his time in geomorphology. He made many contributions to understanding landscape evolution, erosion, river incision, and sedimentation. Perhaps more germane to tonight's lecture, he also was a pioneer of planetary science. And he was the first to understand that lunar craters are caused by impacts, in part by establishing impact geomorphology using empirical studies on impact cratering here on Earth, which could be something like throwing a baseball into a sand and seeing what the effect of the baseball was on how the sand's ejected and the depth of the hole that's made. Anyway, oddly, he was also an explorer of Crater Lake, which was formed by a meteor, as we now know, but despite the fact that he was on top of how craters are formed on the moon, he didn't think Crater Lake was formed by a meteor. So anyway, interesting irony. Mr. J.H.C. Coffin and Mr. J.J. Woodward read portions of letters from Dr. B.A. Gould, director of the National Observatory at Cordoba in Argentina, giving an account of the progress of that institution. And then Mr. J.J. Woodward himself made a verbal communication on the Woodbury photorelief process, exhibiting Woodbury prints of photographs produced by Mr. J. Carbutt at the establishment of the American Photorelief Printing Company for the medical history of the war being the Civil War. In his opinion, the minute details of the negatives were more faithfully preserved by this method than by the Albert-type process, and it was therefore preferable when natural objects of delicate texture were to be representative. It was also well suited, in his opinion, for reproducing photomicrographs, as shown by several proofs, which he also exhibited at the meeting. Woodward was a surgeon and a considerable scientist. He served as an army surgeon in the Civil War. He autopsied Abraham Lincoln after his assassination and John Wilkes Booth after he was killed. He co-authored a definitive medical history of the Civil War. He developed many dye stains for use in medical pathology, a field he helped found, and he pioneered the use of photography in microscopy, establishing the field of scientific photomicrography. He made numerous presentations to PSW on photographic techniques, such as the one he made at this meeting, and Woodward served as PSW president in 1881. The last talk of the meeting was by E. Frisbee. He reported on a method for calculating the ratio of the circumference of the diameter of a circle, of the circumference to the diameter of a circle, that is to say pi, which was accurate to 30 decimal places, which was pretty good for the time. The method was partly published in the journal Messenger of Mathematics. I don't know if that's still published. Frisbee was actually quite a notable mathematician of his day. And with that, we'll turn to tonight's lecture on the prospects for life and human habitability around nearby stars. It's my pleasure to introduce tonight's speaker, Carey Lisse, Senior Research Scientist at the Applied Physics Laboratory at Johns Hopkins University. Carey's been active in the fields of astronomy and physics for more than 3 decades, which is hard to believe. He's very young looking. He started out as an instrument scientist on the Nobel Prize-winning COBE project before earning his PhD. He then moved from the very edge of the cosmos that concerned COBE to studies of astronomical objects closer to Earth, writing his dissertation on comets detected in the COBE All-Sky Survey. And he has since then continued to focus much of his work on comets. He was involved in the Deep Impact mission from start to finish, in particular using the Spitzer telescope to observe the dust excavated from comet 9P Tempel 1 by the impactor, which is the part of the Deep Impact mission that actually crashed, deliberately was crashed into the comet. In addition to studying comets in our own solar system, Carey is also searching for asteroids and comets around other stars. Finally, he's done significant work on X-ray emissions from planets and comets, and he may tell us something surprising about what might be a planet, but maybe isn't a planet in our own solar system about X-rays. And in conjunction with this work, he served as chair of the Comet ISON Observing Campaign team. Among many honors, Carey has received several awards as part of the COBE team, the JPL Stardust flight team, and the EPOX 1 flight team. He is a recipient of a Space Telescope Science Institute Science Merit Award, a Space Foundation Space Achievement Award, a Johns Hopkins Applied Physics Laboratory Special Achievement Award, and he was awarded the Isaac Newton Institute Visiting Fellowship at Cambridge University. He is an AAAS Fellow, and his name is now on a heavenly body, at least figuratively. Asteroid 1226, Carey Lisse. Can we see it?
Yes, you can go to the telescope.
Ah, okay. Carey speaks widely about planetary science, and he has appeared in numerous documentaries about planetary science and cosmology. He earned a BA in chemistry at Princeton and an MS in chemistry at UC Berkeley, and an MS and a PhD in physics at the University of Maryland. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Carey to the podium.
Again, thank you, and thank you for having me here this evening. I want to dispel a simple problem that happens often the time. My real name is Carey Michael Lisse. I am called, no, it's fine. I'm called Casey by my family. So if you hear either one is fine. My friends and family usually call me Casey. I also want to point out a young gentleman who I work with at APL, Kirby Runyon. I think most of you know him. In fact, he's got some of the things I'm going to ask him to distribute around the audience. And Kirby, if you want to send the stickers around, you can do that right now. I have some New Horizons and Osiris Rex stickers, only a few. I don't have too many, only one each if possible. And Kirby and I have been working together on the New Horizons mission. He and I work, oops, I should get the water. We're both working currently. We've just flown by Pluto, and we're on our way to the next Kuiper Belt object. So I want to tell you that right now, this evening, I'm extremely glad to be here because I belong here. I'll explain why. And I also shouldn't be talking tonight, and I'll explain why too. The reason I should be here is I come from a medical family, and as you've just heard, I have degrees in chemistry and physics, and I'm a practicing astronomer. So I'm what the old English in the Victorian era would call a natural scientist. I've always been curious, why is the sky blue? Why do rivers meander? What makes things work? Why is our universe the way it is? And as Einstein would put it, I'm endlessly curious. I'm always asking questions. And it's fun that we can answer a lot of these. And so what you're going to see in the talk, and in my career, I've now been doing this for more than 30 years. It's kind of scary. I'm getting up there. And I remember still being as young as Kirby here, that I'm really good at taking things from disparate fields and putting 2 and 2 together and coming up with 4.5. And some of the reason I'm giving the talk tonight is because I have a medical background, because as a kid I went with my father to the Smithsonian, and I always wondered about the fossil record. I always see different fossils, but I never got an idea what they looked like in time and a linear scale. I also fell in love with the rocks there, and I'm an amateur rock hound, and I have lots of gems and minerals in my house. And I actually do astromineralogy now with my chemistry background. But anyway, a lot of these things are going to come together in this talk. Now, hopefully what I'll do is the talk up on... Uh-oh. Okay, I also don't want to use scary with the words. There are a lot of words here. This is the conclusion slide. Because I'm going to actually read you the conclusions, and I'm going to show you a lot of pretty pictures and a lot of slides, then we're going to come back to the conclusions again. So you don't have to remember any of these. But the important part of this talk is you're going to hopefully walk away with an idea of how long it took for the Earth and the Moon to grow, and for life to develop, and for what this means for stars near us. How old are they? What kind of life is on them? And I'm going to give you a few factoids, which will hopefully make you think. And if you like this talk, I'm going to point you to a very good paper by a fellow named Howard A. Smith. It was written in American Scientist. I have a slide that's actually going to show it. And it was called Are We Alone? And it was extremely well written for the educated layman. And I strongly recommend you read it after this discussion. Okay, so I think that's most of the preliminaries. So what I'm going to talk to you about and hopefully promulgate is the fact that we have stars in the sky. Anybody can look up at night, and that's one of the things I remember doing as a kid too, was wondering, there are stars up there. I wonder if they have planets. One of the most important things that we found in the last 10 years, the Kepler mission has shown us, and I'm probably going to say this later in another slide. I should tell you why I shouldn't be here in a second, is that we no longer ask the question, where could there be planets? We say, there's a star up there. Where are its planets? We think that every star has planets now. That's pretty amazing. So if you go out after this lecture, if you learn nothing else, if you go up and look in the night sky and see the Big Dipper, or you see Polaris, or you see the Orion's Belt, ask yourself, I wonder what kind of planets are on those stars, and if there's life there. And that's the kind of thing I hope we'll talk about tonight. Okay, the reason I shouldn't be here tonight. I spent the last week proposing. I have literally just written proposals, and I was up all night. Proposals that were due at 8 this morning on European time. And I was just asking their XMM satellite to go look at Pluto to verify the X-rays that we've just detected from Pluto using Chandra. And it's not part of this talk. If you want to talk to me about it later at the question and answer period, we can hear it. On Monday, I delivered 2 proposals to the IRTF telescope on top of Mauna Kea, Hawaii. One asking to look at the alien architecture star and see if its light from it is changing and see what's going on there. And the other is to follow up on Kepler stars that we think have planets around them in their habitability zones, which we're going to talk about in this part of this talk. So we're going to actually try to probe and understand those stars, because it's important to know what kind of light the stars are putting out and exactly what's going on with those planets and those stars, because you often hear things like, oh, we found a planet and it could have life. It's in that what we call the Goldilocks zone. Well, you got to kick the tires some more, because as I'm going to show you, if you think about our own system, we have Venus, we have the Earth, we have Mars. Venus is actually in the region where water should be kind of okay. We know Venus can melt lead on its surface. It isn't just how far it is from the sun. It also has a lot to do with its atmosphere. So these are things you have to kick the tires. So whenever we hear things like, oh, we found a planet that could, size of the Earth can bear life, then you got to think a little bit more about exactly what's going on. People get a little excited. As we like to say in the exoplanet business, every planet is special. Okay, so hopefully you've been reading a little bit of the summary. We now know that there are about 100 billion stars in our galaxy. And each, because of Kepler, has likely formed its own Earth-sized planet. We're close to it, at least on 10%, 20%, maybe up to 100%. The universe, just some simple age numerology, is 13.8 billion years old, according to WMAP. That's our latest numbers. Our galaxy is about 12 billion years old. Okay? So the galaxy formed about 1.8 billion years after the beginning of the universe. Took a little bit of time, but not too long. And our solar system is only 4.56. So the galaxy was around for a good 7, 8 billion years before the sun formed. Been around for a while. The sun, if you want to think about it, is probably a 3rd or 4th generation star. A lot of recycling, burning of helium, hydrogen, supernova, explosions, and then recycling into stars before we came along. I'm going to show you a slide that shows we live 2/3 of the way out from a weak central black hole, which means we don't have too much radiation coming from the center of our galaxy, which is good for life. And we live in the suburbs. I'm also going to talk about stars and basically give you an idea of the reason why the stars that you see in the night sky. I just told you to go look up and think about their planets. Well, here's the bad news. Those stars that are beautiful, blue and white, that you can easily see on a beautiful night, those are pretty much what we call the rock stars. They're really giant, big stars, most of them. They're really hot, and they don't last very long. Again, in a nutshell, our Earth is 4.56 billion years old. I'm going to come to this, but the human race is maybe 4 million years old. The Earth had to be around for 4.5 billion years before you had anything that looked anything remotely like us. Those bright stars in the sky are only going to last a few 100 million years before they go boom. They're not going to have enough time to make life. So it's really the big, bright, blue-white ones, forget it. You need kind of the yellows, you need the oranges, you need the ones that live longer. Another way of putting this, and I'm going to, again, talk about this in a slide or two, is that mass is destiny for a star. The more mass you have, the faster you burn, the shorter you live. Okay? So you really want the smaller stars. Okay, and I mentioned the fact that with Kepler, we've just gone through an incredible age. I got into astronomy on the COBE project, so the Cosmic Background Explorer, where we went from all kinds of theories about how the universe could be formed and using general relativity, trying to figure out from Einstein, Lemaitre, et cetera, whether we had a steady state or a Big Bang, how the universe started and how it was evolving, to actually going out and measuring the radiation, finding the Big Bang explosion. What can the relics from that? Realizing we had to start in a big explosion. So we went from theory to measurement. Well, we've been talking about planets for years and trying to wonder why every system should kind of look like ours. Sun, you put all the rocky ones right next to the star because that's where none of the volatiles and ices and water could last. Then when you get far enough away where liquid water and solid water is stable, then you start making the really big planets. Then you have the very edge of the solar system where there's just nothing left. Kuiper Belt. We found no solar systems with Kepler that look like that. They all look very different. So theory is very nice. Measurement is what's important, observation. Okay, I'm also going to talk about the fact that the Earth is a highly differentiated, very unique object with an overabundance of water on the surface. If you actually take the mass of all the water that we know, which is 1 ocean's worth of mass on the surface, we think there may be up to 10 in the mantle, and you divide it by the total mass of the Earth, it's 1 part in 10 to the 4 or 10 to the 5. It's tiny. If I gave you a rock that was that dry, you'd say it was dry as a bone. Our Earth is actually an incredibly differentiated body where all the really light stuff, all the water has come to the surface. Hard to believe when you go out in a swampy Washington evening or you go play on the seashore, but the truth of the matter is we actually have very little water on the Earth. What's interesting to think about is where did all the water go? Because when we look at Europa or any of the moons outside in Jupiter and Saturn, they're half water. There's water everywhere. And water is a very common thing and easy to make. So we're very lucky that the Earth melted and all of the really heavy stuff. In fact, go ahead and just pass that around. I'll talk more about this later. Kirby is going to pass around a piece of nickel-iron asteroid. This is a piece of a metal core. This is what the center of our Earth looks like. Or under lower pressure, it'd be a lot hotter. But this is basically a piece of an interior of a planet. And so this, what you're holding now, everybody's going to get to touch this, used to be between Mars and Jupiter. And it was formed with just a few million years at the beginning of the solar system. That's what you have in your hand. It's called Campo. It's Campo. It's actually from Argentina. It was discovered by conquistadors. And you can look it up on the web if you like. You can also buy it. That's not too expensive. I don't sell it. So we also are lucky that we have a giant moon. This moon does things like gives us tides, but it also stops us from wobbling a lot. If you look at Mars, I'll talk about this again. I'm giving you all the punchlines right now. Remember, you don't have to memorize this. You're going to see pretty pictures later. Mars tilts every million years. It tilts over 30 degrees. That's the equivalent of London going to the North Pole every million years. We don't do that. It's because the moon takes up all that wobble. The moon helps us a lot. We have plate tectonics, and we're actively creating and turning over our surface, which means we have flows of carbon and water. But it also means that we actively also keep ourselves warm, too. I'll explain that a little bit. And we're also shielded by a magnetic field, so the solar wind, we don't get the sun's radiation right on top of us, which means we don't mutate every 5 minutes, and we can actually have DNA and somewhat stable lives. Life is also, when you look at this Earth, it's found in an incredibly narrow range, even though we find life everywhere. And I'll talk about the fact that life is literally everywhere, and bacteria are doing very, very well, and they're the dominant species, even though we think we may be. In fact, I had a nice conversation this dinner about that. But the life that we know of so far, it goes from maybe 10 miles down to 60 miles up. But that's as far as we've looked. But we find it everywhere. We find it under Lake Vostok in the Antarctic. We find it in drill holes it's eating rock. As long as there's a little bit of water, bacteria can eat rock. Wherever there is a place where there's fuel to burn, the same way a car burns gasoline, we burn food. And we add oxygen, and we burn it into carbon dioxide and water. And that's how we extract energy. If life has a way of doing that, be it from dioxins or hydrogen sulfide or methane, if it can exploit that energy and build structures and defeat entropy, it will do it. We also, again, if you compare this number, I'm going to show you the picture this thinnest rind on a body that's 7,600 miles across. We just live on the narrowest rind of the surface of our body. So Venus and Mars, I'm also going to talk about in our solar system, and they're failed harbors for life, and I'll show you why. So the other thing I'll mention, this also came up at dinner, somebody else mentioned it, but I was going to point it out. Life, the first great pollution event, yeah, sure, maybe we're doing global warming, we're putting stuff in the atmosphere, pods and ozone. We weren't the first to do it. The cyanobacteria, the reason why we're having this, one of the reasons we're having this discussion is because cyanobacteria, over billions of years, ate all our carbon dioxide and turned it into oxygen. That is not normal. If you look at Venus and Mars, they are nitrogen, carbon dioxide, and water atmospheres. They don't have free oxygen. So thank you. So next time you can hug either a tree or a cyanobacteria, please do. Pardon me. So another thing, and again, there's a lot of biologists, and this is where I know enough to get in trouble, and hopefully I'll learn some more from the people in the audience. Life is experimented with a huge number of forms of life, different forms, over 4.5 billion years. But interestingly enough, there's one great common denominator. The only place we find life actively metabolizing, actually growing, doing things. It can sporulate, it can go quiet, but it needs liquid water in order to grow and transform and reproduce, metabolize. It can turn off in the lack of the water, but it needs it. This is important when we think about could there be planets out there where there's methane life or ammonia life or whatever, or if you like, if you're a Star Trek fan, Horta life that lives off of silicon. As far as we know, you need liquid water. That seems to be a universal requirement on the Earth. What's also interesting is the Luca, and I'll explain what that is, was a thermophile. Somebody had the bright idea to look at the tree of life and look at all the branches that were coming off the basic, the common denominator to all our ancestors, all the life, and they're all thermophiles, which argues strongly not for a tidal pool origin of life, but for a hot smoker down at the base of the ocean. I want to point out that Earth life was blue-green, squishy, and single-celled for the first 4 billion years. So bacteria pretty much ruled, and those are the guys that did the pollution, and they still rule if you look just by total mass. Not by who's building highways or cities, but just by simple mass. And then I will gross you all out by explaining that where bacteria are right now in this room. If you want basically every single stinky, bad smell you can think of, it's all bacteria eating stuff and putting out products. Multicellular life has gone through at least 4 unique stages and huge upheavals due to giant impacts. We've seen bug-eyed monsters, then pill bugs, then giant lizards before us. We're batting cleanup. We're the fourth to come along. And that's interesting to think about, too. Okay, I'm going to touch on this. This is brand new in the last month. I'm only showing this. I'm going to get to it later. But we have a planet discovered in the next door star system. I'll explain why that's interesting and important. So let's start with some pictures. I've just given you the whole talk. This is just going to explain it in pictures. And thank you for putting up with that. So here's our galaxy. If you're looking down on it, it's a big pinwheel. You'll notice that we live, and this is not exaggeration, 2/3 of the way out. We live in the suburbs. The galaxy, the densest part of the galaxy is towards the center, and this is where stars first formed and where they evolved the fastest. They evolve rather slowly out here, and they evolve almost not at all at the very edges. What this means is the very first stars in the galaxy, which is 12 billion years old, they took their hydrogen and helium, and what they do is they burn it, and they make ash, and the ash is heavier elements. So everything that's in our bodies, we're 75% water, which is hydrogen, but it's also oxygen. We have organic, carbon. We have lots and lots of calcium and phosphate in our bones. None of that was in the, very, very little of that was in the original universe. It took stars burning the hydrogen and helium and making those atoms before you can make us. So it took 3 generations here of stars making stuff, burning it, throwing it out either in red giant winds or in supernova explosions before you came along with the sun, which had enough rocky elements to make rocky planets around it. And that rocky planets eventually had enough stuff to make us. So this is what we call galactic evolution. So one of the things I'll get into is a little bit of where are the neighbors. We live way out. We're in the burbs, or maybe even in the provincial country. And if you want to think about it, we're really in the burbs. This is the Hubble Deep Field section. Each one of these is a galaxy. We think there are now as many galaxies. There's 10 to the 11th, 100 billion galaxies out there. Each one of them may have 10 to 100 billion stars. So there's probably 10 to the 22 stars, each with a planets. That's a lot of planets. What I think about this picture, if we could turn the lights down, is they look like seashells on a seashore. It's just gorgeous. I could look at this for hours. So this is one of the things I wanted to show you, and I'll spend a minute or two on this. This is the timeline that I always wish I had in my mind when I went to the Smithsonian. So here is now, here's us. And you've probably seen a little bit of this. This is the time, see that little symbol here? That's the time where things like humans were around. So this is a linear scale. The Earth formed 4.65, they round up 4.56 billion years ago. Moon formed about 100 million years after that, okay? And life shows up somewhere around 3.8, 3.6 billion years, right after what we call the late heavy bombardment. We'll get to this, but I'll cut to the chase right now. When you look at the moon is a fantastic piece of archaeoastronomy. This is, by the way, the part where the talk gets screwed up because I've been proposing. I don't remember exactly how this should go. My short-term memory is shot. But please bear with me. When you look at the moon, one of the things you remember from this talk, when you next full moon, if you go out and you look at it, and if you have binoculars, it's fine, you're going to see craters all over the moon. The moon is just covered with craters. The fact that the moon is there to begin with and is so big in our night sky is because it's a relic, we think, of a giant impact between a Mars-sized body when the Earth was about 80% full. So the moon itself, just being there, tells us about the Earth forming. Almost all of that body came in and became part of the Earth. But it was also a bit of a skim, it wasn't a center shot, kind of hit at an angle. You're a ball and kind of hit like this. It scraped off the surface, and some of that stuff went into orbit around the Earth, and within a few thousand years, it coalesced and became the moon. So when you look up at night, just the fact that there's a moon there and it's big and fat tells you there's a giant collision. Then, about 600 million years later, it got covered with craters. If you look today, you'll see them. They have not changed. We were just as hit and just as beat up. We had all the craters the moon had because we're about 4 times bigger in radius. We're also got 20 times the gravitational pull. We would have actually gotten just plastered. All those craters are gone because we have weather and we have plate tectonics. What's really interesting is right after that impacts all those craters on the moon, that's when the first evidence for life shows up on Earth. Folks are split on this one. One, could it have been due to the fact that, I like to call it Purina life chow. Did whatever hit the Earth and the moon bring in water and organics, bring in enough stuff that life could start? The other argument is that's the last time the Earth and the moon got the holy expletive beat up about, just got clobbered. And after that, the impact stopped, and life may have been already here, but there was no more giant impacts. Work done since that actually shows that we still have a bunch of giant impacts. So I really think it's more the delivery of organics. And as I'll show you a little bit later, the energy, everybody's idea that the Earth was a glowing molten ball of lava when it first formed is absolutely correct. The energy it takes to assemble the Earth is about, just simply, without any velocity, just simply bringing the rocks together, is 10 times the energy it takes to melt it. So everybody's idea that the Earth was a glowing molten ball is right. And what happens when you cool off a glowing molten ball? You get lava plains, and you don't grow food on them. You don't grow organics. You don't grow life. What happened here, most likely, is you brought water and organics in from comets, from asteroids. Okay, so then you come along. First life starts after about 1 billion years. And then for 3 billion years, you come along and you've got single-celled, single-celled, single-celled. Then you have the eukaryote revolution. Single-celled, single-celled. Finally, only 500 million years ago, do you actually get multicellular critters and you start getting things that look like animals and plants. The longest time period, the huge stretch in here, and thank you for bearing with me, you're just talking bacteria. And that's critical because I'm also going to show you very soon, the average star in our neighborhood is 3 billion years old. It's probably stuck somewhere. If the record of life on Earth is the way life forms everywhere, that's a big if, then most of the life around the stars we see are stuck in here. On the other extreme, if you want to talk about what's going to happen in a bit, 2 things are going to happen. One, in another 5 to 6 billion years, the sun's going to go red giant. The sun's middle-aged right now, halfway through its lifespan. The other thing is, you probably heard, the Andromeda Galaxy is also one of the few galaxies, rather than the expansion of the whole universe, that's coming towards us. It's going to collide with us in about 5 billion years. So you take your pick which one's going to happen first. Now, most people actually, I should point out, the Andromeda Galaxy isn't going to cause the end of life as we know it. It's going to cause the end of the galactic structure. Stars aren't going to hit each other. It's just going to mess up the spirals in the galaxies. But it's also going to create a lot of new stars and maybe supernova near us. So anyway, this is 5 billion years. I wouldn't worry, wouldn't sell the house. We're not going to last that long. We got a while. Okay, so thank you for living through that, but that's one of the most important things. So what I want to do is, I should say one more thing about this. Next time you go to the Smithsonian and you see when they show you little sea lilies, or they show you crinoids, or they show you dinosaurs, or they show you trilobites, I'm going to show you again where each one of these show up. And what I want to point out is the vast majority of the time, you're just talking about single-celled critters. And then the trilobites dominated about 500 million years ago. So most of the time, Earth was either barren, or just dominated by single-celled algae and bacteria. That's the normal stage of life on our Earth. We're an exceptional anomaly, if you will. All right, so now I'm going to talk a little bit about the stars near us. I'm going to talk about what stars we've got, and this is the big question in exoplanets today, not just finding out all those planets out there. Everybody loves to find the next planet. They're all special for some reason. Either they're in a double star system, or they're in the Goldilocks zone where water is liquid, or what have you, or they're as heavy as iron or uranium. But what we really want to know is, can we find Earth too? That's what an awful lot of us are looking for. Can we find the next Earth around a G2V, a sun twin, a solar twin? So I'm going to talk a little bit about the stars near us and the planets we found. Okay, I think these graphs are a little bit complicated, and for tonight, I'm not sure I'm going to go into too much. This number of 710 planets, this is a very old slide. We now have from Kepler more than 5,000. And what I'm showing you here are distance from the star versus the mass of the planet. This is Mercury, this is Mars, Venus, and Earth. And you'll notice that none of these detections, in this case, this is for microlensing, I believe. And also, there's 3 different ways to find planets. One is what we call radial velocity, where we see a star, and we actually see the star move back and forth a little bit. And that's because there's a planet moving around, and the planet actually makes the star wobble at the same time the star makes the planet. The star doesn't just sit there pinned to space. The planet can be big enough to make the star move in a little circle too. So if we can actually see that back and forth motion of the star, we can actually get the mass of the planet. The second way we find planets is what's called transit observations, and this is what Kepler did. Does anybody remember when Venus went across the face of the sun just a few years ago? Actually, just a year ago. Well, if we had been sitting back far enough, I think with only one group actually did this, we could actually see the light from the sun drop by a few millionths. It actually blocked out simply. If we were just looking at the whole sun and measuring all its radiation and not blasting our telescopes and our detectors, because that's a lot of radiation, we would actually see a tiny drop. And that's because Venus just covered up some of the light. Well, this is what Kepler does, just does from very far away. And the third way we do is what's called microlensing. We can actually watch a star and a planet go in front of a distant galaxy, and we can see that galaxy's light change. You can actually use general relativity to focus the light. And these are all the planets that have been found so far. And you'll notice that we can find Jupiters and Saturns up here. Uranus and Neptunes are kind of challenging, but we're getting to them. Finding Earth and Venus and Mars are very hard. All right, so this is what Kepler has done last year. And here's an idea. Here's Earth. Kepler is looking along one of our spiral arms. Here is a plot of the planet's size. And here's its orbital period. To give you an idea, Earth lives over here 365 days and would be down here at 1 Earth. And you'll notice that the Kepler planets are all a lot bigger. Haven't been really good. It's hard to find Earths around other stars. We can find a few, and we can find ones that are really close in. But it's hard to find ones out by us. And this is what we call the size-frequency plot for planets. And you may have heard a lot about hot Jupiters, these planets that are so big they're right on top of the stars and they're roasting. They're easy to find, but there actually turn out to be very few of them. Most of them turn out to be here in the smaller planet size. Not surprising, it's easier to make smaller things. If you want to know what Kepler was, can anybody knows what the Northern Cross is? Can you find it in the sky? No? Kirby does. Kirby got a few people. Kepler literally just took the world's giant CCD array and just stared at the sky in the Northern Cross for 4 years. And it looked there because there's a million stars in this field. It's actually in the galactic plane. And it just watched all these stars and saw if any of them dimmed. And dimmed by a few parts in a million, that means a planet was going across the star. The probability for doing that is a few percent. And Kepler found on the order of thousands of these. And it all works out. The numbers work out fine. And from that, you can figure out that every one of these stars probably had planets. Kepler systems look something like this. This is one of the famous ones, 62E and F. So this is the 60-second system they looked at. Little letters mean that there's a planet. This guy had 1, 2, 3, 4, 5 different planets. And they're all sitting there about the distance from Mercury out to Mars. And in the habitable zone. What one has to be careful about is that most of the planets that we've here described are around stars that are not like us, ours. When I mentioned to you that it's very easy to see a wobble if the planet is close in and heavy, you can also see it if the star is a lot smaller than our sun, but the planet's farther out. It doesn't have to be so heavy. And the smaller a star is, the longer it lives, but also the cooler it is. And there are stars that are called K stars, and there's also stars called M stars. And they are very dim. And you have to be very close to them in order to have life going on, and that's what I'm going to show you here. So this is something called the Hertzsprung-Russell diagram. I don't know if people are familiar with this. Basically, what you're seeing here is that a star's mass is its destiny. The smaller amount of mass you have, the dimmer and fainter you are. Another way of putting this is if astronomers often use something called the blackbody series. If you imagine you put a piece of metal in a fire and you heat it up a little bit, it's the first thing it's going to do is going to get red hot, kind of a cherry color. You heat it up some more, it's going to start getting yellow hot. You heat it up some more, it's going to get white hot. You heat it up really, really, really hot, it's going to get blue-white. Stars are doing the same thing. They're basically, their effective temperature on their surface go up and up and up as you add more mass. Another way of putting this is that a star's mass, this mass it starts out with, it's pretty much its determiner of how hot it's going to be on its surface and how long it lives. Heavier mass ones live very, very, very short lives. But they're also the rock stars. They're the ones you easily see. They're the blue, white ones in the sky. These guys down here last for the age of the galaxy, the red ones. Our sun lives right there. It's going to last for 10 billion years. These guys are going to last for 20 or so. Then as you go up and up here, these guys are only going to last for a few billion. These guys are going to be hundreds of millions. Why is this important? Remember that history of life on Earth. In order to get us, in order to have this conversation we're having tonight, you had to last 4.5 billion years. The only stars that do that without blowing up or turning into white dwarfs are guys here and down. Okay? So that just throws out all the beautiful ones you see in the sky, all the ones that make all the noise, make all the pretty constellations. We don't think they can make life. They're just not going to be around long enough. If you also think about the spectrum, what it would be like to stand on the surface. So this is the spectrum of our sun. It peaks in the yellow-green, which is why when you look at the sun, it looks yellow. It's got a lot to do with why plants are green and the light that we see during the day. If you were around one of these F stars that are going to last for maybe 3 or 4 billion years, and maybe at the outer chance, if they're really efficient making life, would have some, or just even some bacteria, they're going to have a very blue-white sky. Whereas Ks and even Ms are going to have very reddish skies. The other point that's important is on this scale is luminosity. If you want to be a planet where water is liquid and you want to be around these guys that lives forever, plenty of time to make life, you're going to have to be almost right on top of the star. You're going to be inside the orbit of Mercury. And that means you're going to be suffering from the star's radiation when it puts out solar wind and has flares. And also you're going to be suffering what we call tidal effects. You're probably going to be locked, so only one side of your planet stares at that star the whole time. It's going to be very interesting winds and weather. Okay, this is a plot I love to show, especially if there's anybody in the audience that likes science fiction. This is actually from Larry Niven, his Known Space series. And he's taken it actually from a RAND study. Sun is right here. This is a hex, I don't know if you can see it, this is a hex map. And what you've done is projected in 3 dimensions. You've taken the distance from here to any other star in hexes is the radial distance. So we projected 3 dimensions into 2 dimensions. You don't worry about whether it's up or down or sideways distance, it's just the total distance. So what am I trying to say here? Alpha Centauri is right here. That's the first and closest system to us. The color of the little ball here is the kind of star that lives next to us. The reason I show this image is you can immediately see the vast majority of stars around us are the little red guys. Okay? That's another reason why people try to find exoplanets around them. But again, little red guys have to have planets right on top of them, which is going to have nasty flares, and you're going to have to live under the ocean. It's going to be tough. What's amazing is that right next door, right next to us, the closest system and the one we will first get to ever, Alpha Centauri, has almost an identical twin to the sun. And it's 6 billion years old. So life had time to form there. This is a coincidence because I've asked more than one stellar astronomer, wow, did we form together? Because we now know that stars don't form by themselves. They form what we call stellar cocoons. They typically form 300 or 400, 500 at a time in a little cloud. When the cloud collapses, and they disperse as the galaxy rotates. Well, what I've been told is the galaxy has rotated plenty of times, 20 times or so since we formed, and Alpha Centauri did not form with us, even though it looks like it's got a twin of us. It just happens to be passing by at the right time. What's interesting is, and what's on the next slide, is that this is also the system which was discussed that have a planet in it, and I'll explain that in 1 second. I want to show you that there are some other solar-type stars. You probably heard of Beta Hydrae or Tau Ceti. Some of these show up, 82 Eridani. These all show up in science fiction. But there's not a lot of them. The other reason why, when you look in the night sky, the brightest star in the sky is Sirius. That's because it's the closest A star. It's big and bright, and it isn't going to have life, it's going to last long enough for life, and it's not very far away. And that's why it's the brightest star in the sky. Anyway, that's a fun plot. I showed it to Larry Niven at a Balticon, a science fiction convention, a fantasy convention. He liked it. This was announced just a month ago, Proxima Centauri b. Alpha Centauri is a triple star system. Another thing about these stars, I went kind of fast, the average star in the galaxy is not a singleton. The average star has 1 or 2 or 3 brothers and sisters. Even though it formed a natal cocoon and lost most of them are in binaries or trinaries. We're actually exceptional that we're alone. Alpha Centauri is a 3-star system. It's got a star like the sun, it's the biggest one. The next one is what we call a K2, which is just a bit redder and oranger. And the third one's a little red guy. So the third one lives here on this plot, it's down here. I think it's actually might even labeled, there's Proxima Centauri, it's right there. That's the one they just found a planet around. And they've been arguing the planet is close on top of this star, Proxima Centauri, which is the closest star to us. It's of the 3 in Alpha Centauri, it's even closer than the 2 bigger ones. That's what they're trying to show you here. Here's Proxima, there's Alpha and Beta. And it's got a planet, and the planet's close enough to the star that water could be liquid there. We have no idea of how big the planet is. We know it's about 1.3 Earth masses, at least, so it's not too much bigger than the Earth. We know that this system is about 6 billion years old. Here's the name of the paper if you want to read it. And if you think about it, we think it's tidally locked, meaning this hemisphere, the same way that we always see the same side of the moon. This part of the planet is always staring at the sun, so noon is always in the same place, and it gets pretty hot there. Most likely, the place life will form is probably not right there, but probably around the terminator, the day-night line, and maybe towards the poles. It's fun to think about this, but we also don't have any idea about its atmosphere, and I'll talk about that in a little bit. Okay, so I think since we'll move along a little bit, here is the average age for stars. Remember that plot I showed you with all the stars near us? The average age for stars near us, somewhere between 2 and 4. It's about 3 billion years. Remember where life forms and how long it takes. That means blue-green squishy. Okay, we're over here. Alpha Centauri is over here. So it's not the majority of stars that are near us that could have life. Okay, now I'm going to talk a little bit about necessary but not sufficient for life. Again, habitable zones, people argue about this a lot in the exoplanet business. Just because water could be liquid doesn't necessarily mean there's life there. This is our own, okay, so here is a plot of star size, I was talking about that before, versus orbital distance. So here we are at 1 AU, 1 astronomical unit from distance from the sun, and here we are around a G star. So as you get to smaller and smaller stars, you come closer and closer in. This blue band is where water could be liquid. Just simply from the way I like to put it for the older folks in the audience, if you ever had an easy bake oven, you know how you get closer to a light bulb, it gets warmer, you get farther away, it gets cooler. Just think if the average temperature just depends on how close you are to that light bulb at the center of your solar system. Okay, so you can imagine that if the light bulb gets dimmer, you have to get closer in. As simple as that. So, that's not the whole story. This is a very busy plot, and if I put people to sleep before, this one's really going to, but I'm going to summarize it quickly. This is the plot or curve where you'd expect temperature if it was all just due to the sun's insolation on the planet. This is the actual temperature, this is Venus, when you add in the greenhouse effect. It isn't just how close you are to the light in the easy bake oven, it's also how well you hold the heat. One of the things I wish people would teach more, has anybody been in a car in the summer with the windows up? You know, even though it can be, or just now, just go outside. I was just in the car today when I was getting ready to come here, and you know if the windows are up, it suddenly starts getting very warm and very hot pretty quick. That is the greenhouse effect, happening right there. It's nothing more or less than light can come in, it gets absorbed by your car's interior, gets converted and warms up the interior, gets converted to infrared radiation, and whether you know it or not, those windows in your car are black to infrared radiation. It does not get out. Venus is extremely good with its atmosphere at taking all the light from the sun and never letting it get out again. So even though if you put the Earth where Venus is, it would only be about 100 degrees Fahrenheit warmer. Notice I'm using English units, but it would only be about 100 warmer. Most people think that as soon as you move the Earth in, everything boils. That's absolutely not true. When you boil off all the CO2 on the Earth, when you take all the calcium carbonate, all the chalk, and all the seashells, and you take all the carbon dioxide and you put it in our atmosphere, we turn into Venus. This is one of the things that gives astronomers a nightmare about global warming. We are way, however, far away from this happening, but this is the kind of thing that is a nightmare. On the other hand, I give a long talk, and I'm going to make this very brief. I want to point out that the history of our civilization looks like it started about the time of the end of the last ice age. which is very interesting. Humans probably don't do very well making cities and civilizations if there are glaciers all over the place. As a civilization, we most likely we're going to have to learn how to mess with the weather sooner or later anyway, probably in 10 or 20,000 years, not now. But we were going to have to do it if we didn't want the next glacial cycle to come back. What I want to say, long story short, not ignoring any politics or religion or anything, we were going to have to learn as a species how to deal with the weather. We are doing a somewhat uncontrolled experiment right now with warming up the planet. But I would argue that we do better, even though I don't like it really hot outside, probably better if they're making sure there's no glaciers and being a little too hot than being too cold. But we're also going to have to worry about the fact that if there are no polar caps, if you look at there's a very nice map in National Geographic published of 77 million years ago when there were no polar caps. There was also no east coast of the US. Everything from the Piedmont up to the foothills of the Appalachians is underwater. So you take what you get. On the other hand, Canada and Russia are going to be extremely habitable, where it's now all ice and tundra. So it's change. Our species is very good at change. This shows a little bit about that. Habitable zone also depends on the age of the star. This is our sun right here. Our sun is going to warm up in a few billion years. So even before it gets to red giant, our oceans are going to start boiling just because the sun is getting hotter. As the sun gets older, it burns and makes ash. It also has to get hotter at the center in order to burn hydrogen and helium better. And it's just going to warm up. And it's been doing this. It's about 30% hotter and brighter than it was when it first born now. So we know the sun is going to change. So one of the things we might do, and it's kind of funny, this is an old presentation given by Alan Stern many, many years ago. He was wondering if the sun warms up past just a few billion years, but when it becomes a red giant, would we move out to maybe Uranus or Neptune after they warm up so much they lose a lot of their ices and a lot of their things that are hard to live with, and they become more habitable? Or would we move to the Kuiper Belt when it gets maybe warmer? We're going to have to move, but we have plenty of time. So here's another thing that's also interesting to think about related to this. Yes, I took this slide from Deborah Fisher, who's a Star Trek enthusiast. But this is an important question if you haven't heard of it before. It's called the Fermi paradox. Enrico Fermi, father of the atomic pile and one of the original pioneers of atomic energy, and also namer of the neutrino, was also a big fan of what we call napkin science in science, which is basically taking very simple ideas or very simple numbers and doing a quick calculation and coming to an important conclusion. And this relates basically to where are they? Where are the aliens? Because if you do very simple numbers, galaxy is 12 billion years old. We know the size of the galaxy is on the order of a few 100,000 light years across. Even if there's no such thing as a warp drive, which currently we don't know of anything, you can't go faster than the speed of light. You should be able to go from one side of the galaxy to the other side in easily a very small fraction of its lifespan. So we should have been visited. So in other words, you just simply go out there and go put, put, put at 10th of the speed of light. You should have been go from one side to the other and back and forth a few times. So Enrico asked the simple question, where are the neighbors? Here's that article I was talking about. We'll talk about it. Maybe the answer is that there's a whole bunch of possible answers. One, maybe we're an elder race. We're the first guys here. Another is maybe we live so far out in the suburbs and we haven't been intelligent for very long that maybe people came here a long time ago, or critters, or alien species, and there wasn't anything to look at. They're not interested. Another possibility is they're here and they're not talking to us because they don't want to mess with us. And there's a number of ideas. But this also touches on what's called the Drake equation, which I'm not going to talk about too much. But in the Drake equation, there are lots of terms, basically simple probabilities. One of the probabilities is how frequently do stars have planets? We've just answered that. The next one is how frequently do planets make life, make intelligent life? How long does that intelligent life last? These are all terms you have to multiply together. When you do that, I'm going to talk about this really quickly. I think reasonable numbers for this, and depends on which numbers you put in their arguments, there's easily somewhere between 100,000 and 10 million intelligent species or intelligent civilizations right now in the galaxy. It's not hard to believe. Because there's 100 billion stars and they could all have Earths. The problem is that we're far away from each other. There's no faster than light travel. It's not like you can't talk to the neighbors very easily. Maybe simply one of the answers. Another answer is, remember, most of the stars near us are only 3 billion years old. So the neighbors are most likely blue-green squishy, and they're not very good at conversation. Don't forget, it's only been a little over 100 years that we were able to have radio technology, that we could actually hear signals from off of the Earth. So it's not like we could 200 years ago, we couldn't have done a search for other life. So it takes the intelligence and the ability to understand and manipulate energy, electromagnetic energy, in order to talk to the neighbors. I'm sorry, I could be talking a little bit better. So let's go look at our own system and remind you of what we got here. Sun, Mercury, Venus, you're here. Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, and the Kuiper belt. We know of life here, well, at least we call it life. We think there may be life around Europa. More and more indications you've got an ocean world with an ice shell on top of it. And then we're going to talk about whether is it possible. And what we're finding, now we've found water in, what, 10, 20 different ways, Kirby, on Mars? I mean, one of the jokes at work is, oh, how is NASA going to discover water on Mars this week? But the point, while that sounds facetious, think about it. You know, when I was a kid, when people were arguing, was Mars have canals or was it all deserts? I mean, you think about it, this is great progress. There's water in so many different ways. In fact, currently, just earlier this year, people are arguing that there probably was a global ocean on Mars. And I'll show you a picture of that in a second. Let's talk about the Earth. Here's that picture I wanted to show you. Here's the Earth. There's the crust. We live on the tiny little top of the crust. We live on the plus or minus, minus 10 miles, plus 60 miles. That's the atmosphere. That's it. That's where we know life. The rest of this is inactive, as far as we can tell. But that's our wonderful pale blue dot. Water is incredible. I've already mentioned that you need liquid water for life, but water moves heat around. It makes the greenhouse. It's a major greenhouse gas. We don't think about it. Nobody's going to take water out of the atmosphere. We need it. But it does a lot of the energy capture. It also is very good at controlling our heat, our planet. Most of the heating that's happened on the planet so far from global warming is going into the ocean. It has not gone into the atmosphere. The atmosphere is so much easier to heat up because it's so undense. The ocean is what's really absorbed all the heat. And that's what's scaring most people, is that the ocean, just a few more degrees warming, what people are really worried about is there's something called clathrates. They're methane water ice composites that sit at the bottom of the very cold ocean. If they warm up just a few more degrees, they'll let all the methane go, and methane is a really efficient greenhouse gas, and that's what some people are really worried about. But again, if you're a good swimmer, or if you want to live in North Dakota, stop worrying. You know, Northwest Passage will be open, lots of oil, there'll be change, but it could be very interesting. Just don't live in the Seychelles or Bangladesh. Honestly, people are going to have to change, and Florida is a sandbar. Unfortunately, there's not much you can do about it. New Orleans and New York you probably can protect, but Florida is going to be tough. There's lots of things that water does, and also a lot of geochemistry is mediated by it. And I'm just going to show very briefly. This is the phase diagram for water. So this is pressure versus temperature, and here's our wonderful Earth. And you think about it, I talk about water, we put these hiding around, but just think about it. You can have a day where there's snow on the ground, you can see it melting where there's liquid water, and you can even see some fog above it. You can see all three different forms of water on one day. They're stable on Earth. Or you can imagine that you know that there's icebergs up north, we have oceans, and we know that we have steamy air down here. Again, all three forms of water are stable on Earth, one place or another. Mars, right now, all you can get is either solid on the ground or gas. You don't have any liquid water easily seen. Maybe there's stuff flowing underneath, but in the past there was. Venus, all you can have is hot gas, water, some water in the atmosphere. Nothing stable on the ground. And as far as we know, you need that liquid water in order to have life. So we don't think they can harbor life right now. I'm going to skip this, but basically just, you know a lot of this just in real life. And this is just a nice pretty picture showing all the different things that water does. And if you think about it, it's a lot. Runoff, hurricanes in Florida, very timely. Water storage in the atmosphere, snow. I mean, there's this whole cycle with energy, with also geochemistry interaction. Water is very dynamic, and it sculpted the surface of our planet. It doesn't do that on Mars or Venus. Okay, I've just gone into water a bit. Now this is a laundry list, and this usually drags on, but I just want to give you a little highlights. Again, if anybody wants to copy this talk, you're welcome to it, especially if I'm going fast. There are so many things we think, just writing down, that could mean you need life. And one of the things I believe personally, but I'm not sure I can prove it, is I think that life might be very exceptional. I told you that it's very possible the Drake equation, there could easily be a million plus or minus an exponent different civilizations. Another possibility is that we're just really, really lucky, and it's very extraordinary. Maybe there's just a few. Because you need all these things. You need to be right distance from the star. You need to have the right star that lasts long enough. You also don't want to have it so small that it lasts forever, but you're right on top of solar flares. And those little red guys flare a lot. That's something they didn't, by the way, if you read the Proxima Centauri paper, they don't talk about the fact that it's a flare star and it flares every day. So if you want to be life on that planet, you've got to be under the ocean or under a rock and hiding from that star a bit. They're very good at kind of hiding that a little bit. You need a stable planetary world. You need to have a planet that doesn't tilt or doesn't have a very extreme seasons. Think about us. We have a 23-degree tilt. Okay, if this is the plane of the ecliptic, the sun's here, the earth's here, we tilt this a ways. And just that 23-degree tilt is what gives us our extreme of summer and winter. If we had a much more extreme tilt or really crazy orbit, you can imagine we could have very violent seasons. So what would be better, of course, was if we had a perfectly perpendicular tilt, and then we could have like spring all the time. You need to have the right planetary mass. If we're too big, it's very hard to make life. Gravity wouldn't let things get big enough. You need to have enough mass and heat in order to have plate tectonics. We think Mars is a frozen world. Maybe you need a Jupiter-like neighbor. We're still arguing over this one in the business that helps clear out comets and protect us from getting hit by comets. Maybe some people think that maybe life started on Mars and then came here. Maybe you need a smaller neighbor for it, or a bunch of neighbors, and maybe they'll seed each other. I mentioned plate tectonics. I'll show that a little bit more. You need to have a large moon. You notice how this is a long list. We're very lucky that we have the moon, and the moon is very special. If you think about it, Venus and Mars don't have a moon like ours. They don't have this big giant moon in the sky. Venus has none. Mars has two tiny little rocks that may have been grabbed from the asteroid belt. They're nothing. The moon is very special, as I mentioned previously, but it's still very special. Maybe you needed giant impacts, a few in order to not wipe out your life, but enough to bring Purina life chow. You needed a right amount of carbon. It turns out, again, the Earth's surface is carbon poor, and maybe some of that a lot of that had to be brought. I can go on, but the point is you also needed biological evolution. Somehow you needed to make photosynthesis so you could eat your CO2 that's very normal and turn it into oxygen so you can have animals and people like us so we can breathe and talk and eat food. You needed the right kind of galaxy, which had enough heavy elements, but not too small, nor elliptical or regular, which isn't making any stars. So there's a long list here. And I can show you, oops, why did it go that way? No. Sorry. Anyway, so you can see that there's like 20 different things there we can think of that make the Earth unique. And I'm going to just show you a few of them. Here's plate tectonics. Here's what our tectonics in a nutshell does. Hot core, you get convection, just like you get when you boil water. And what's happening is the mantle is going up. Hot mantle gets heated near the core. The surface of the core, by the way, is almost the same temperature as the surface of the sun. It's hot down there. And that's due to radioactives and also the residual heat from when the Earth formed. And rocks is boiling, it's convecting. It's not boiling. It's coming up. When it hits the surface and come out, it actually can make, that's the lava and the magma you see in volcanoes. Comes in, cools off, dumps its heat, goes back down again. These plate tectonics, that process moves the plates on the surface around. And it's very easy for us as human beings who are used to, if you think about it, most of us in this room, our time scale that we're familiar with are maybe to our great-grandparents, to our grandchildren. So we're good at thinking personally on time scales of maybe 100 or a few hundred, at most a few hundred years. That's really pushing it. We don't usually think in terms of geological time. We can write it down in numbers, we can use equations. This is what the surface of the Earth looked like. I need to read this for you. This was, I believe, 800 million years ago. That's 700. That's 150 million years ago. This is current, and this is what's going to be in the future in about 100 million years. I'm sorry these didn't come out. But the surface of the Earth and the plates haven't always been the same. And in fact, I've just learned, I think Kirby taught me or somebody, is that it's actually thought to cycle. That all the continents will come together, make supercontinents, and they'll break up again, and then they'll come back again. So it's easy for us to think that it's always been like this, and that's absolutely not the case. Why is this important? Well, besides the fact that it means life, when it's a single continent, life can go back and forth and communicate, it also means the weather is going to be very different here. When you're a big giant landmass, you can imagine you only have so much coast. We have a lot more coast right now, a lot more interaction with the ocean. Here's the picture of the moon I wanted to show you. And here's our moon that's helping us survive, not tilt too much. But this is the picture of the moon with all those craters on it. This is false color, and the bigger ones have been circled. And you'll notice they're just all over the place. They're covered. The moon is what we call saturated in craters. And this is what we looked like, along with the moon, 3.6 billion years ago. We were just as plastered as this. Okay? When we look at the Mars, it's interesting. This is getting back to that gentleman who many years ago first understood that craters were due to impacts. This is what Mars looks like. Okay, so this is what we call a cylindrical projection. So this is south of the Mars' equator down here. This is north. You'll notice there's craters, looks to be highlands, and there's lots of structure down here, and there's nothing up here. This is what's called the Mars crater dichotomy. It's thought now, there were two arguments. One, Mars just covered with lava. let me back up. In geology, on planetary surfaces, when you see a surface that has no structure, it's typically young. It's been covered over. All the stuff due to craters and mountain building and earthquakes and et cetera, and when it's gone, it almost always means it's young. Something's happened to it. In this case, it was either due to lava flowing over everything, or it was due to an ocean. And now we have very good arguments now it's an ocean. In fact, they see what look like ancient tsunami borders on the edge here. So Mars most likely had a northern polar giant ocean. Here's another fun question when you're trying to think about life on Earth. Remember I mentioned the sun was only about 70% as bright when it first started out? We should have been an ice ball. Earth should have been just totally covered in ice. The temperature difference between now and the last glacial period was just a few degrees. And the sun was almost as hot as it is now. One of the real questions in the business has been, why aren't we always an ice ball? Because this is also a runaway process. Once you cover the Earth in ice, it's really reflective. It doesn't pull in much heat from the sun. It stays cold. The same way that if we go the other way, extreme, we'll stay warm because we absorb a lot more. It's called our albedo, the ability to absorb. You want to think about it just, another way of putting it is, if you put a hot black thing on a sunny patch of ground, it's going to get really warm. Whereas you put something that's very shiny, it's not going to get as warm. Simply, it's the Earth's ability to absorb energy from the sun. And so the Earth should have been a frozen snowball for a long, long time. We do not see this in the geological record. We think what happened actually was that snowball Earth was rescued by volcanoes and carbon dioxide coming from inside the planet, which gave us a strong greenhouse that melted the ice. And that right now we're actually oscillating in this kind of period where we try and get glaciers try to take over, but then you'll get CO2 and it'll reverse the process. It goes back and forth. And so we've actually been seeing oscillations in the last few million years. But this is an interesting question as well that people are arguing over. I think I'm going to strip this off and go past this. I just want to argue is that very, very, very young stars are extremely X-ray active, meaning we have to worry about that when the Earth was brand new, it was getting bombarded and really clobbered by the sun. So that first billion years where there's no life, it could have just been not only because no organics and water was brought to the Earth, and not because of impacts, it could be because the sun was corking off all the time, just like Proxima Centauri will do to its planet, and just irradiating, blasting apart any life that formed. Here's an example of, okay, so here's the Earth. This is what we have currently. Here's our beautiful magnetic field. Here's the sun trying to throw particles and all kinds of nasty stuff at us, but we have the nice defensive magnetic field. And this is also, magnetic field is what makes the aurora. When the particles from the sun come here, they are channeled by the magnetic field. Most of them go into what's called the geotail, but some of them can follow the lines and they fall on the poles. And that's why you see the aurora at the north and south poles. And what you're seeing is those charged particles hitting the atmosphere, hitting the oxygen and nitrogen in our atmosphere. And just like in a fluorescent light, well, these aren't fluorescents, it's the same process. They're just exciting those and making them glow. So you can think of the aurora as giant green and red and white fluorescent lights. Here's the plate tectonics, and when I get into that, Mars doesn't have that magnetic field, so we think it's lost. It had an early atmosphere. And in fact, most of the studies now argue that Mars may have been wet and just as warm as the Earth was when it first formed. But one of the things that happened is it got its atmosphere just stripped off by the constant bombardment from the solar wind. Mars was also so small. Let me skip through this. I'm going to actually want to show this slide and go back, sorry. Mars is also so small compared to the Earth. This is the Earth. Mars is only about a tenth. That's not right. It's about a factor of 3 or 4 smaller in radius and about a factor of 5 in mass. 6 times 10 to the 24, and I think it's about 1/10 the Earth's mass. It was so small, it didn't have enough radioactives that Mars basically froze out in the interior. It doesn't have the plate tectonics because it has no heating mechanism to make things convect. Its crust does not move around. It doesn't get warmed from the interior. It doesn't have a lot of the processes that we have. So Mars basically cooled. Also, if you work out, a body that's smaller than the Earth has a surface to volume ratio. The surface of a body goes as its radius squared. The volume goes as the radius cubed. The amount of radioactives inside the planet go as its total mass, as the radius cubed. Basically, what I'm trying to say is that Mars is smaller, had less total heating from radioactive in the center, and had a proportionally larger surface area. It could get rid of the heat faster. So Mars cooled off and froze. All right, I wanted to show this slide, and I apologize for being a little back and forth. This is an example of failed biosphere. This is not Arizona on a cold winter morning. This is Mars. Kind of looks like it could be maybe Arizona with some frost. This is carbon dioxide ice. This is not water ice. But it's not dissimilar. And don't forget that when NASA trains people to go to Mars, astronauts, they usually go out to Arizona. They go to the top of Mauna Kea. They go to these places that are dry and volcanic. I showed you this before. Again, Mars lives over here. Water and liquid is not stable on the surface. I showed you this before. Again, I show it a bunch of times just to give you an idea. Again, we're over here. No life. Life shows up. Life is single-celled for so long, then you get the eukaryotes. Then you start making lots and lots of oxygen. Then you get the Cambrian explosion. And here's where I get the sun start showing. And so there is evidence for water on Mars, multiple evidence. Right here, these are river channels. Here's the picture of Mars I was threatening to show you. Here's the southern highlands and all the craters and structure. And here's the northern. Oh. And here is a good shot of the northern hemisphere. And that's why we think there was an ocean on Mars. Kind of cool. So ours could have been a place where life formed, but it just didn't last long enough. It wasn't stable for long enough. All right, so here's the timeline again. Let's talk a little bit about life on Earth, pardon me. And again, we're not the first or the second. It's easy for us to think we're dominant, we've been here forever, and that's normal for every species, probably, otherwise you don't survive dominate. This is a slightly different way of showing you. One of the things I'd like to point out here, see how wide this is the dinosaurs. If you ever want to get rid of some of our hubris, dinosaurs in one form or another lasted for 120 million years once they developed that lizard hip. And they went through various different species, but they did very, very, very well. Anything that looked like man walking on two legs, maybe 4 million years if you're generous. We've got a long way to go before we're as successful as the dinosaurs. Now, we probably built better cities and theme parks, but hey. So what I'm going to talk to you about a little bit is here, again, no life, lots of single-celled life. Animals start coming along, and then I'm going to show you the three ages of different kinds of animals dominating. Okay, I guess I'm going to talk to you about this one first. Let's go back to the very beginnings of life. Lots of words here, but this is where we're going to talk about the LUCA. LUCA stands for the common denominator. It's basically what we think was the critter that gave rise to the bacteria, the eukaryotes, and the archaea. It's what seems to me have all the common DNA. And I should be careful. We have people in the audience who know more about this than I do. I know enough to get in trouble. What is smart, let me come back to that in a second. Somebody went along and figured out, oops, here's the LUCA, it would be right here. And they went and figured out what kind of environments. This is a broad brush picture I'm showing you here. This is the more detailed one. And here's the root. Remember, we live way over here. We're way along a branch. So what I want to get at or say is that somebody had the smart idea to figure out what kind of environments all the root branches like to live in. They were all what we call thermophiles. They all like to live near boiling water temperatures. That's very interesting. Because for the youngsters in the audience, when I was a kid, most people argued persuasively that water probably formed in tide pools near oceans, where there was kind of maybe a place where there was a little basin, some water could slop into it. A lot of the water could dissipate, but it can enrich the concentrations of chemicals in that water. And with tides, with the moon, some water would come in, some fresh materials, and maybe eventually life form there in interactions with the rock. Well, that's a good hypothesis, nothing wrong with it, it seemed interesting. But what it seems instead is that all the early life looks like it like really high temperatures. And where do we find high temperatures? We find it maybe in geysers in Yellowstone, and there's plenty of interesting thermophiles here. We also find it at hot smokers at the depths of the ocean. And I'm going into this for a second. I'll explain why. One of the other things I'll say about life, in general, sweeping terms, all life that we know on Earth has, let's look at it from a chemical point of view, brings in raw materials, burns it, makes energy from that, and creates structures. And does this in some sort of cellular fashion, creates a membrane where there's inside and outside. Actually, be careful, viruses possibly are borderline definition, but they still have to live inside a cell. But in order to metabolize, so this is the way that we eat food, and we excrete. That's very normal. And the thing is, from a chemist's point of view, you would say is that however you can get free energy out of a substance, and you can use it in order to build structures and defeat entropy. You can, the normal process of destruction, decay in life, this is how life is built. And it also needs that water that I mentioned. I had a fascinating talk with a guy named Mike Russell who works at JPL. And I know this looks a little busy, but basically what I'll point out is he argued to me, and I went a tidal pool guy before I had that dinner with him, is that where you're seeing hot smokers, what's happening is you're getting magma, which is reduced, can give up electrons, can get burnt, has a lot of interesting chemicals in it. It hits water, which is oxidizing in the ocean. And here's a membrane, here's a boundary. And you can get a lot of chemistry right here. And in fact, groups have now shown that you can make simple organic molecules. You can actually do what looks to be steady state chemistry, possibly simple, maybe simple metabolism. You also get a lot of deposition of iron sulfides, and they make cellular structures. They make what look like little cells. And you can get membranes. And what's also interesting, and this is where I get enough trouble, and I'll stop, is that iron sulfur proteins in our bodies are some of the most primitive proteins that we know. So it's all very interesting, a little hand wavy here, but it's interesting to think about this. And what this is, again, looking at this from chemistry, this would be what we call a steady state situation or system, where we bring in materials, a reaction happens, and we put out products. So this could be where the first life-like reactions happen. Why is this important? Well, I was always very skeptical of going to Europa, Jupiter's moon, which seems to have this ice shell and maybe an ocean under it, because there's no way you get light in there. There's no way you can get photosynthesis. Maybe you get some chemotron. But at the bottom of its ocean, it's tidally driven, and there's lots of tides and tidal heating. Europa probably has the same kind of system going on. So if life forms like this, not in a tide pool, Europa could have formed primitive life, just like we did. Okay, for the biologists in the audience, and for those who aren't, just to gross you out, make you think. Just some numerology. 100 billion stars in a galaxy. Seems like an awful lot, right? Well, on our own planet, we're never going to go swimming again. There's 1 million microorganisms in each milliliter, each cubic centimeter of that ocean that you're swimming in. If you ever swim off of Hawaii and gotten a cut and gotten some algae or some coral in there, it's kind of fun. I have. There's 1 billion microorganisms per gram of soil. So it's going out and getting dirt from the backyard. If you do the sum and try to just estimate, that means there's a ridiculously large number of microorganisms on Earth, and there's even more viruses. So life, as I mentioned, while we only found it 10 miles down and maybe 60 miles up, it's everywhere. Life has been very good at finding and covering our planet. Here's an estimate of the different kinds of life animals versus fungi, plants, protozoa, chromista, ones that we know of versus still to be found. And you'll notice that the percentage depends on which kind of beasties we're looking at, but we've still got a long way to go to catalog all the life just on Earth. And here's where hopefully you didn't have dinner too long ago. If you want to think about this, is the kind of thing just over a weekend or when I was thinking, there's bacteria everywhere. They are by dominant right now. They are the dominant mass on the surface of the Earth. And they are doing very well if that's considered your definition of dominant species. So here's a piece of moldy bread. The reason it goes bad, the food goes bad, is because there are bacteria, there's mold, there's fungi on them. And if you just let it sit, it's going to go bad. If you leave a Petri dish just out with some agar on it, it's going to grow stuff. Here's a lady. She's got E. coli in her gut. So does her dog. She's got stinky feet, maybe, and that's where. She needed to brush her teeth to get rid of the biofilm. There's all kinds of bacteria. That is a slime mold right there that she's got in her garden. That's a bunch of amoeba. I can go on, but you get the idea. There are bacteria in life, there's everywhere. Now there's work studying on us that there's hundreds of different species of bacteria colonizing our skin in various places, be it feet or underarms, whatever, different things. And you know that every morning you have to brush your teeth, and there's a reason. It's growing on the food that you ate previously. So there is bacteria everywhere. Another interesting fact, we think about 1 trillion cells in the human body, but there's 10 times more little tiny, much smaller than our mammalian cells in your gut. And there's a lot of DNA in there. So what we're also learning is that your gut has been colonized. And I think current research is arguing and showing that communication, what happens in our gut, how we support those E. coli, is actually going to be more and more important. We're probably going to learn there's an awful lot of synergy going on. A different way of putting this is I read Michael Crichton's Andromeda Strain as a kid. And I always tell this story. And that is the book that taught me that the Andromeda strain, or like Ebola, is a very stupid and very, very poorly adapted species because it kills its host right away, and it dies. E. coli is one of the most successful beasties on the planet. Because every one of us, sorry, whether you like it or not, are getting along just fine with E. coli, also the beastie that invaded our cells and made mitochondria. They're symbiotes. They're getting along with us, and we're working with them. From their point of view, we might be just walking agars or test tubes. We keep them alive. And so it's the symbiotes, the ones that work together, have done very well. Okay, so give you an idea of the 4 different regimes of life. In the Cambrian, you had trilobites doing very, very, these are the bug-eyed monsters. So these are not imagined pictures, these are actually what we think fossils. Imagine every monster movie, nightmare scene, no bipedal symmetry, 4 limbs. Life was trying everything when it first started making animals. Just incredible. And going back to the picture of the camera, and I know this looks like it's a cartoon out of a book, but it's actually pretty interesting to go look at some of the species that have been found. It almost looks like life was just trying to see whatever it could and just throwing it against the wall and seeing what would stick. Things settled down later, and this is where the pill bugs, trilobites, were dominating, and you had your anemones and your sea lilies. So when you go to the Smithsonian, bug-eyed monsters live here in the 500 million years ago. And then you come on the Silurian, these all die out, and then you come along to the trilobites, the pill bugs. They die out, and then you get the dinosaurs. And these are the dinosaurs, the fish equivalent of the dinosaurs, and they live for 120 million years. Then they get wiped out in the Chicxulub impact on Yucatan, and then we come along. Well, we're not fish, but basically anything that can survive that impact. So right now, our current idea is that there have been at least four, people argue, I believe 5, different massive extinctions, 1, 2, 3, 4, 5. And you can actually correlate these pretty well with what we think are impacts that have hit the Earth, have dramatically changed the environment. And you can look for these boundaries and try and see impact residuals on the surface of the Earth. So we're getting back to astronomy. This is where astronomy is important, where we need to think about those impacts on the moon, impacts on the Earth. And this is a little dramatic, but if we have a body that's bigger than 60 miles across, it's bigger than the atmosphere. This one's a little exaggerated. But the point is, even a mile or 2 mile across body, that's poking pretty far up. That's as big as a mountain. It's going to hurt when it hits. And most likely it's going to hit water, and it's going to make tsunamis. But there's good news. This little beastie, the tardigrade, he can survive anything. He can go out in space and be desiccated. I understand, although while talking over dinner, that he can't survive too much radiation. We figured he'd be the best astronaut in the world. You can send him. He's a little water bear. He lives in fresh water. He's kind of like about the size of a copepod and eats little plants. And so this guy, APOD stands for Astronomy Picture of the Day. So you can actually go look him up and learn more about the tardigrade. So if we ever mutate him or give him a brain, again, he's about this big, he'd make a great astronaut. How much time do I have left? Okay, I'll try to move on. So one of the things we're going to do is we're finding all these exoplanets. Again, the goal is whoever finds Earth 2, whoever finds one Earth mass body around a sun-type star with a 300-day orbit, that's gold. You're going to hear Nobel Prize and people screaming and yelling, and we got to go there. So how are you going to find it? Well, you need to go and find what you think, for all our techniques, that one Earth mass body. You want to look. We know how to look for that kind of yellow star that we're at, but how would you look at it? How would you figure out if it's got the right atmosphere, which I've hopefully argued for you is also as important? Well, I worked on the Deep Impact mission. We put a hole in a comet in 2005 and saw what was inside, stuff that hadn't seen the light of day since the beginning of the solar system. Comets built the planets. And one of the things we did in between comets is we turned around and we stared at the Earth. There is a movie here. Epoxy, the same spacecraft that went and hit a comet and then went and flew by another one called Hartley 2, also turned around and looked at the Earth. This, by the way, is the moon. This is really cool. I'm not going to try and show you the movie tonight. You can go online. You can see the moon, and this is real color, as far as we can tell. There's blue-white Earth land masses. That's the brown moon, and you can actually see it rotating around the Earth. It's really cool. And these are looking in different wavelength bands, and we're actually trying to see whether we could see the signatures of life. Could we see oceans? Could we see the continents? If you look very carefully, this is Africa, right there. The movie is fascinating. I really recommend reading it.
Well, please show it.
Maybe, I'm a little worried because I'm running out of time. I will show it to you if I can get, oh, actually, it's on my computer, not on this tick. This is what we call a light curve. We're actually watching the Earth turn. And this is what we saw in terms of the light, different colors. And what you're seeing here is the oceans vary a lot, especially when land masses come and go. Here's the moon here. We also saw a big dip when the moon blocked a lot of the light from the Earth. So if I can, I'll show you the movie. The other thing that's important, and this gets argued about a lot in the astrobiology business, is how would you tell if there's life on given the atmosphere? If you looked at our own atmosphere, and this is actually the spectrum of our Earth from our spacecraft. There's a number of things you could do. You can look for, remember, we've got carbon dioxide, we have water, lots of it. We have little tiny dip due to oxygen. This is the thing, if you remember, oxygen is not normal in a terrestrial planet atmosphere. carbon dioxide, water, and nitrogen is. But it's not a very strong resonance because oxygen is what we call a homonuclear. It's a symmetric molecule, so it doesn't have much of a vibrational transition. That's a problem. So it's pretty weak. There's also a really, really weak little bump due to bacteria. It's called nitrogen oxide, N2O. The other thing you can do is look at what's called the red edge. You could look for all the green plants. And they're green because they absorb red. So you can look for this little bump over here. It's at about 700 or so. And people argue over that too. Here's that N2O thing. See that? It's a little tiny thing. And this is when we're on top of the Earth. We're most likely never going to get that in a planet that's light years away. So I argue that O2 or ozone, which comes from oxygen, when it's really easy to see, is most likely to be a biomarker. The other thing that's cool, if you just take the colors of the planets, as measured by deep impact and others, you simply take, these are called color ratios. So this is the ratio of blue ultraviolet to green. This is red to green. If you manage to do that, astronomers are really good at this, by the way. We collect butterflies. Slight, and I apologize. So a slight tangent here. I'm trained as a physicist and a chemist, and those disciplines, if you want to make an experiment, test something, you set something up, you vary one variable, you see how things change. Change the concentration, reactant, put in gasoline or kerosene and see if it still burns, blah, blah, blah. I mean, like that. You can't do that in astronomy. You can't make a planet or a black hole or a galaxy in your lab and change one variable. It doesn't happen. You can't do that. So instead, in astronomy, the philosophy is you collect lots and lots of samples. You collect butterflies, and you look for trends in them. You try to see how they act. So in this case, what we've done is we've taken all the planets in the solar system, and we look to see if their color ratios separate them out. And sure enough, you notice the Earth is way up here. And that's because we have the blue water in the oceans. And we have our red, and also, mainly that, it's mainly oceans. None of the other planets are dominated by water oceans. The rocky planets all down here look very red. You're not surprised, the moon is brown red, Mercury and Mars are also red, and even Venus, surprisingly enough. The giant planets are all rather, well, they're reddish, but they're also kind of bright in the ultraviolet too. Only the Earth. So one of the simple things you can do, okay, why am I going on about this? So spectra are wonderful. They also are very, very expensive to get in time, and it's very hard because you break the light up into lots of tiny little bins. This is color photometry. It's very simple. It's just like the red, green, blue on your TV, or if you were just to take a picture of this room and just put a piece of red cellophane in front of it, you can get a lot of light pretty fast. I don't need to take the spectrum of anybody. This is an easy measurement to do. So I've already talked about this, and I'll just show you the spectrum, and maybe it's overkill. But our atmosphere is very oxygen-rich and carbon dioxide poor. And this is what our atmosphere looks like compared. So here's the Earth. This is, at least I got this right. This is Mars and this is Venus. And I've been saying this again and again, but I want to show it to you again. What we see on Earth, this is ozone. That's 9.7 microns. Okay, that's created by when O2 gets split up by UV and turns into O3. You don't see any of that on either Venus or Mars. You see CO2. And this is the CO2 that becomes optically thick, and this is your greenhouse gas right here. But you also see a bunch of water for us, and you don't see any of it, almost none in Mars, and you see a little bit of it in Venus. But we're dominated by lots and lots of water in our atmosphere. Everybody's got carbon dioxide, but we also have the ozone. I think this actually might be a very good biomarker. Let me skip over that. We're almost done. This is the article I recommend. If you like any parts of this talk, you're curious about any parts of it, it's called Alone in the Universe. This is by Howard A. Smith, not Howard K. Smith. He was a famous newscaster. And this is an American scientist. It's available online. It's a wonderful article. It basically argues, bottom line is that given everything we've done in the searches, given all the fact that we've sent out radio signals over the last 50 years or so, it looks like really out to a few hundred light years, there's nothing out there. There's no life, as far as we know, intelligent life that can talk to us. But it's only a very small sphere around it so far. It's nowhere near as far as the Kepler stars that I showed you earlier. And here's those conclusions. So thank you for staying awake, most of you. You remember I showed you pretty pictures? And again, just think about the fact that there are hundreds of billions of stars in our galaxy. And if you'd like to motivate this, next time the galaxy is up at night and you're in dark sky and you can see the Milky Way, pick up some binoculars and suddenly you're going to see lots and lots of stars jump out of it. And remember that everyone's got an Earth-sized planet, maybe, most likely. We've got an old galaxy. We should have been visited, but we don't seem to be, so it's a good question. We live in the burbs, and we are now finding planet after planet after planet, and this is just the beginning of planet hunting. I mentioned the fact to you that Earth is highly differentiated. We're lucky to be here. We have all the water on our surface, which is good for us. If it was spread evenly out throughout the Earth, we wouldn't have our life as we know it. I mentioned that we need the moon to keep us happy, plate tectonics to keep us warm, and a magnetic field to keep our atmosphere here. Life is, again, living on the surface of the Earth, and we live on the rind of the orange. Venus and Mars may have tried to have life, but they don't have the conditions right now. And finally, I also mentioned, once life got started here, it's done all kinds of cool things. It's eaten, it's made all the oxygen we have. It has made all kinds of forms. It is most likely started, we think, probably at a hot smoker. And it was most likely very simple and blue-green, or at least single-celled, for 4 billion years, where animals and plants and things that we know are very recent innovations. Okay, and then finally, I just mentioned a little bit that there are 4 unique stages, and most likely punctuated by dramatic equilibrium or stochastic impacts and things that cause the life to disappear and then reappear in a different form. So I guess the takeaway message there is, hopefully we'll last as a species very long, but if we don't, if for any reason we do something to ourselves, nuclear war or something happens, I doubt that life will end on Earth. It just might come back in a different form. It may not be us. I don't mean to sound depressing, but life will abide. It has so far. And thank you so much for listening.
Thank you, Carey. We have time for some questions, 5, maybe 10 minutes. If you have a question, you have to raise your hand. You'll notice there are 3 people walking around the room with microphones. When the microphone comes to you, please stand up, tell us your name, tell us if you're a member, you're not a member. If you're not a member, sit down. No, I'm just kidding. There's no penalty for not being a member. And ask a question. Don't give a speech.
Don't be shy. Part of my job is to give back and talk and teach.
So let's see hands. We have one up here in front, Lloyd. Oh, I have one right there, Lloyd. Question, no speeches. Stand up, please.
He's tough.
Tell us your name.
My name is Chandler, and what a fascinating talk. I'm curious if by popular demand for the movie, could it go forward?
Unfortunately, my computer didn't work, but I was thinking about it. If you go and Google Deep Impact Earth-Moon movie, you will find it. And we could try and do that maybe after the question and answer period. Maybe I can do it on his computer.
Thank you.
You're very welcome. It's fascinating. You literally see the Earth turning, you can see the continents, and you can see the moon going.
We have a question way in the back.
Hi, my name is Jess. I'm not a member, but for kind of intellectual, titillating question, because I've been following on Facebook. I've been following the discovery of the alien superstructure, and so far they said they've found 2, if I'm not mistaken. So they found 2 stars that they can't. The best they can scientifically say is that they can't describe what's around them. But just for fun, what are the chances that it is like something like a Dyson sphere? Just for fun, I'm just asking.
The answer is no, but let me explain why. No.
Can you explain what a Dyson sphere is?
Yes, okay. What's important to point out, first of all, is that as a scientist, one should never take a theory and just poo-poo it. The scientific method is you hear a theory or an idea, you compare it to known facts and see whether it fits the facts. So I actually was fascinated. I learned about the alien architecture star when I was Facebooking with Jason Wright and Tabby Boyajian, who are the 2 discoverers, and chatting with them. And I said, well, have you asked the questions about, have you ruled out everything that's easier and more natural that we know of before you go to aliens? And I was actually perfectly happy. I said this at dinner. If Elvis lands in my backyard in an alien spaceship and shakes my hand, that would be really cool. However, we don't have any evidence for that. What the evidence that they looked at with the star was they looked at it with Kepler, and they didn't see a few millionths of a drop with a planet, like a little Venus going across the sun disk. They saw a drop of 20%. That's ridiculous. Now, imagine if 20% of our sun suddenly got blocked out. It takes something huge to do that. Even when we have comets that come in and die on the sun, they don't block out that much light. So I actually wrote the fastest paper. I asked for observations on a Hawaii telescope, went and looked for any evidence for permanent heat signature. A Dyson sphere is argued, it's an idea by Freeman Dyson, that if we wanted to be an advanced civilization, if we, for example, became 100 billion strong somehow, and we wanted to put that on the Earth, in the solar system, what we would do is somehow take the Earth, which is a sphere, and turn it into a hollow shell. In other words, we make land that's still at 1 AU, the same distance from the sun, with the same equilibrium temperature, room temperature, but we'd make it so it was a giant sphere, with the interior all illuminated by the sun. And that would make a huge amount of land, and lots of people could live there. The problem with this, in terms of observational, is that thing has to absorb the starlight and then reabsorb it, re-emit it in the infrared. Otherwise, it heats up forever and melts and boils and goes away. It's energy balance. You absorb sunlight, you warm up just like a greenhouse, and you emit thermal. We didn't see any of the thermal radiation that we expected above the star. No other group has either. So we know now that there can't be any permanent structure absorbing starlight, and re-emitting it in the infrared. There is no Dyson sphere or Dyson swarm that we know of. The most likely arguments right now, and Wright just wrote a paper about that, there's two. Boyajian argued, could be that a comet came in, a really big thing, probably more like a Kuiper belt object than a comet, and for the very first time went by its star and broke up catastrophically, and literally just covered that star with a huge amount of dust and gas between us and the star. And then went out again. 750 days later, its fragments came in and did the same thing. So one idea is that it's a big eccentric orbit and icy body. The other is that that star just happens to be going through a really dense part of the galaxy, and it just happens to be stuff between us and it, which sounds really improbable, but some of us are coming to that conclusion. I can talk to you about this offline. We've just been doing work on this in the last week or two.
Question over here.
It's a good question, but the answer is no, we don't see evidence.
Hi, Magdalena. I am also not a member. My question was, you talked a lot about life that is, say, actively living, but what about signatures of life that didn't make it? And are you using information, or is that, all your studies also informing scientists here on Earth to, that study how life started here from the conditions that you study in all these planets?
I think you asked a good question. I think it's hard for us not to know. When we sent the Vikings to Mars in the mid-70s, what we did was we actually put little samples into and gave them nutrients to try and see if they metabolize. Trying to look for evidence of life that isn't actively metabolizing. If you remember, there was the argument that maybe I found fossils on Mars in '96, or in Martian meteorites. And that's been going back and forth a lot. Some people argue that the structures were too small to actually have biological structures that can actually metabolize. Other folks have argued it looks like tiny little biological varnishes we see on Earth. I think the jury is out on that. But right now, around other stars, I don't think we have a remote tool that could look for something that is either dead or is not actively metabolizing. Oh, there's one other interesting fact, thank you. If you turn off all the plants and all the cyanobacteria today, within a few thousand years, all the oxygen in the Earth's atmosphere reacts with the iron in the ocean and in the rocks, and goes back to CO2. And basically, all the oxygen disappears. This is sort of the idea, a little bit behind the Gaia hypothesis. Our Earth's atmosphere is oxygen-rich because life is actively making oxygen. If you turn off the life, it goes back to CO2, and the oxygen disappears. So again, I think one of the best biomarkers is either O2 or ozone.
Question over here, and then one back there. No, go ahead.
Oh, I'm sorry. James Griffin, I'm a member. I wonder if you turn the question around and ask about human habitability for colonization on our part by planets in nearby stars. Probably not the nearest, because that's the one we might be jumping away from. What do your studies say about that?
You're assuming we can get there?
I'm assuming the transportation problems could be solved in the next 200 million years, yes.
All right, if assuming that we can get there. Well, no, actually, the group might laugh, but I'm a bit of an amateur historian. When I lecture in a different capacity, I remind people that 100 years ago, most people were still taking either trams or horses to work. The progress in technological innovation, in transportation alone, is amazing. That's just 100 years. Part of me would love to come back in another 100 years and see what technology is like, just to see, and how much farther would we be. So while it may sound facetious, I think 200 million years, that's probably plenty of time for us to somehow, invent space travel, be it sublight or whatever. So let's assume that.
I was asking what you can say about the targets for our colonization.
Well, let's go look for G-type stars, so stars close to the sun, either yellow or a little bit smaller and dimmer, G or K stars. Let's go find them. Let's use our best surveys to find Earth-sized planets, plus or minus 20%, about 100 million miles from that star. And that's where I would start. I would try to figure out what's in their atmosphere. I'd look for signatures of water, because we know water. The same way that let's use Mars as an example. Mars may not have life on it now, but if we go to Mars, most people in this audience have probably seen The Martian. The Martian is literally almost exactly NASA's current road plan for going to Mars. What we would do is go there, we'd bring solar power, we'd be able to split the water into hydrogen, oxygen, use it for fuel, use it for air. We basically take probably a giant Quonset hut or a tennis bubble with a pump, learn how to take that atmosphere and break it up into stuff we can breathe and we can grow plants with. And that's where you'd start. And Mars actually is the first step if you want to learn how to live on other planets. Moon is not. Because it has an atmosphere we can work with and it has water.
Have one last question?
I hope I answered your question a little bit.
I think, Frank?
Hi, Frank Robert, a member. Hopefully this is just to give you an opportunity to go on into the future a little bit with your wonderful talk. I was wondering if you'd want to talk about what you think is the potential from the TESS mission for expansion in our knowledge of the nearby ones.
It's a very good, thank you for asking that. So Kepler did something. It basically stared at one part of the sky, motionless, for 4 years, and watched all these stars and basically let them vary. Kepler, by the way, now can no longer do that. It lost the reaction wheel. Instead, what it's doing is actually moving around the sky and looking at patches for 90 days. And one of the things I did, by the way, and I'm about to talk about 2 weeks in Pasadena, we stared at Pluto with it. We have a beautiful light curve. So Kepler is still alive. It's called K2 now. TESS is different. TESS is not going to just stare at one place in the sky. TESS is going to do what K2 is doing. It's going to go and find the brightest nearby stars, and it's going to look for transits. It's going to look at Alpha Centauri. It's going to look at Aldebaran. It's going to look at Arcturus, and it's going to try and look at the nearby bright guys. And it's going to try and what we call cherry picking. It's going to look for the easy, bright, close, and especially it's going to go after M and K stars, the smaller stars, and it's going to look for light dips. Again, remember, Venus versus the sun's big. If you can go to a star that's a lot smaller than the sun, and you still have a Venus, it's going to make a bigger light curve dip. It's easier to find. But I keep arguing is I think the community really likes to go after M stars because they're easy to find planets. But I don't think you want to live on an M star planet. Again, because you've got a lot of radiation, you have to be on top of the star, and you're also tidally locked, so you've got a really hot hemisphere and a really cold hemisphere, and think about the winds between the two. It's going to be nasty. And you're going to probably have to live under an ocean. So I wouldn't think for habitability, you want to go to an M star. I think you want to go to a G or a K. So yellow or yellow-orange. And TESS is actually going to go and find all these. And both of them together, Kepler and TESS and K2, are going to set up a list of really good systems. And then JWST, which is going to launch in 2018, which is this fantastic 6-meter infrared optical telescope, is going to pound on the really best systems. And it's going to get spectra of the planetary atmospheres. So what I was showing you wasn't pie in the sky. Again, the first folks to find water and oxygen or ozone signatures, maybe methane and CO2, in an Earth-sized body around a yellow star like our sun, you're going to hear an awful lot about that, and that would be really cool. I still hold out hope for Alpha Centauri A. People have looked for a long time to try and find a planet around that, our nearest star system. They have not found one yet, but it hasn't been ruled out either. There were reports of a Venus, a very hot one around Alpha Centauri B, so the second biggest one in the triple system. They have been now retracted. But there could very easily be Earth-like planets in Alpha Centauri that we have not seen yet. And that is the first system. Just like Mars is the first planet we're going to go to, Alpha Centauri is the first system we're going to go to. It's just the closest and easiest to get to. Thank you.
Thank you.
Thank you.
We're going to go
Losing my...
So in appreciation for giving the talk tonight and joining us for dinner beforehand, I'd like to present you with this framed copy of the announcement of your talk. Thank you very much.
Thank you for having me. It was a delight. Anybody picture?
You take this too. All right, we're almost done. Just a few closing announcements. PSW depends on its membership, both for money and to carry out the activities of the society. So if you're not a member, please join, and if you are a member, please think about helping us put on these lectures. You can apply for membership on the PSW website at www.pswscience.org, or if you prefer, www.philsoc.org. That is our older name. So just go to the website and you'll see there's a button there on the home page, and you can apply for membership and become a member. If you're a meetup member, just keep in mind that being a meetup member does not make you a member of the society, and we would like to have you join. Please see membership chair James Heelan, who might be here. There he is. Or our corresponding secretary, Robin Taylor. if you have any questions about membership or providing support. PSW is a nonprofit organization, tax exempt under Section 501c3 of the Internal Revenue Code, and your contributions are tax deductible. Our next lecture, number 2367, will be on October 21st. Well, I'll put it up later. There's a list of, oops, that's not it. A list of upcoming lectures. Oops. All right, good enough. Nope, not good enough. Forget it. Just thank our sponsors. All right. So the fall schedule is posted on the website anyway, and we'll be posting the spring schedule soon. We really have some interesting lectures coming up. The social hour ends at 10:30, after which PSW members and guests go across the street to the Fairfax Hotel Lounge to continue the discussions and also to buy drinks, because you can get alcoholic beverages over there, but not here. If you're interested in going and you don't know how to get there, please see Corresponding Secretary Robin Taylor or Vice President Lloyd Mitchell. Please use the entrances when you leave, the side entrances when you leave the building, and don't go through the club. And I will now accept a motion for adjournment of the 2366th meeting of the Society to the Social Hour. And so Bob Hershey has made a motion. Do I have a second? Carl Merrill seconds. All members in favor? All members opposed?